Okay, people, let's keep going. We're going to start talking about another type of heat capacity, the constant pressure heat capacity. So this will be very similar to when we discussed the constant volume heat capacity. Okay, so as noted, the CV, so I'm just going to keep our twins in mind, right? The twins. Okay, and as a reminder, CV was equal to the partial of U with respect to partial of T at constant V. So we can see CP, the constant pressure heat capacity, is equal to the partial of enthalpy with respect to changes in temperature at constant pressure. Or because we note that delta H is equal to QP, that is the same thing as saying DH equals DQP. Then we can get the above relationship, right? By separating the partials, multiplying both sides by delta T, and thus we get our similar expression for constant pressure. And so just like with changes in internal energy with temperature, if we look at changes in enthalpy with respect to temperature over a very large range, we see something really similar. Okay, so there's a general trend to increase enthalpy with increasing temperatures. And if we looked at this change over a very narrow range, then we would see the slope of that line is a good representative value for the heat capacity, CP, which will be a constant. Okay. But of course, if we look over a very large range here, and just like I indicated before, perhaps this goes from like 0 to maybe 10,000 Kelvin or something ridiculous, right? Some large range. Then CP, we will need an equation to describe it, okay? So that's what we can see in this next slide here. So this is a standard empirical formula for CP. So let's write that down, standard empirical formula. And this A and B, don't confuse those with the van der Waals A's and B's. They are different. And it's empirical because people will fit data to changes in temperature of a material with respect to heat applied, and that allows one to determine the heat capacity experimentally. So when we see things that are determined empirically, that means it was done experimentally. And so here are a few of the recommended values for some various substances, as you can see. So if we are to use this expression right here, there's a couple things that we've got to note. So suppose we want to calculate the change in enthalpy when CP is regarded as a constant. So that's going to be very simple. If we want the molar heat capacity, molar enthalpy, that's going to be CPm times delta T, assuming CPm is constant. And as it turns out, for liquids and solids, so let's write that down, for liquids and solids, CPm is approximately equal to CVm. And that's because, once again, as we've noted, when you heat up a liquid or a solid, it doesn't change its volume by very much, okay? So for a reasonable approximation, right, we talked about how the ideal CV for solids is equal to 3R. So we could say reasonably CPm is 3R for most solids. So in that case, calculating the change in delta H is quite straightforward. We can say 3R times delta T. And of course, if we wanted that in terms of per gram, we would use the molar mass. So now, what if CP is changing? Well, we have to do the following. So our delta H of M, we can't just say CP times delta T. We've got to say CPm dt, and then we have to integrate that sucker from our initial temperature to our final temperature, meaning we'd have to plug this equation into our integral, which would go something like the following, right? Integral Ti to Tf, and then we would plug that in, A plus Bt plus c over t squared all times dt. And now we would perform that integral, and we would get something that looks like the following. So that will be a, and I'm just going to write this as delta t, noting that delta t is its usual meeting, final minus initial temperature, right? So the integral of this becomes a times delta t plus 1/2 times the b constant, and then that's going to be t final squared minus t initial squared, not delta t squared, right? We got to square them and then subtract them. And then now that's going to be minus c over 1 over t final minus 1 over t initial. And then knowing what our temperature change is and using these heat capacity constants, we could calculate the change in enthalpy. So this is, let's highlight that to make sure we've gathered. This is predominantly for liquids and solids. Even though we can see nitrogen gas, it's got some recommended values there. Okay. So really for liquids and solids, this is kind of what we're after, right? And over a narrow range. Again, if the range is large, if there's a large change in temperature, then we need to use this empirical formula. Okay. So as it turns out, the relationship Cp and Cv is approximately equal for liquids and solids, but very different for gases. Okay, so you can see Cp minus Cv equals Nr for gases, or Cpm minus Cvm equals R. So there's a pretty cool proof that we can do to prove this, and we're going to come back to that later on here. So I want to leave this slide blank, and after we've gone down the rabbit hole a few more times, I'm going to come back to this and show how we can prove this relationship for, and I should note, for ideal gases. There is a notable difference between the constant pressure heat capacity and the constant volume heat capacity, and that's 1 unit of R. Okay, more on that in the coming slides. I'll see you then.